Okay, so this is the second video in the series on the characteristics of rolling and slipping with applications to cylinders or spheres. And the idea of these videos is to provide some conceptual details on how to model the motion of a cylinder or a sphere that is slipping during its motion on a flat surface. And there are some conceptual details. There are some areas which can cause some confusions, and hence we are going over some of the benchmark cases to understand especially to understand how the friction force plays out in these scenarios. So we are considering the motion of a cylinder on a horizontal plane, and we first make this was in the previous video, we made the observation that if the cylinder has a forward velocity of V0 and an angular speed, that is a spinning speed of omega naught, then the condition for rolling without slipping is V0 equals omega naught r, where r is the radius of the cylinder or the sphere. So what happens is, if this equality is disrupted, which can happen in two ways. One is that V0 is greater than omega naught r, and the other is V0 is less than omega naught r. So these are the two scenarios in which the rolling without slipping condition is disrupted. And so the purpose of these videos is to firstly show how in these two scenarios the friction force has a different nature. And once we derive the equations of motion and we derive the following results, we want to show some interesting behavior of the motion of the cylinder or the sphere. So first we took the case of V0 greater than omega naught r, and so keep in mind that this means that the initial forward going velocity of the cylinder, which is V0, is greater than the initial angular speed omega naught times the radius of the disk. And if that's the case, we derived the equation of motion, and we came up with, and we could integrate the equation of motion. And what was interesting is that we found out that the velocity as the motion of the disk proceeds under this condition, V0 greater than omega naught r, which causes slipping. What happens is that the velocity decreases from V0 linearly as a function of time, whereas the angular velocity increases from omega naught, again linearly as a function of time. And so we sketched two plots. We plotted the V0, the velocity, and we plotted omega r, starting with omega naught r. And because we know that the velocity decreases whereas the angular velocity increases, we expect a behavior like this: linear decrease in the velocity, linear increase in the angular velocity times r. And there is a point where the two merge; they will be equal. And from that point on, there is going to be pure rolling. Now keep in mind that this is the free motion of the disk. So what happens is that when V becomes equal to omega r, the disk kinematically follows rolling without slipping. By kinematically, we mean that there is no external force in the motion of the disk. It reaches a point where automatically, when the point of contact with the ground, whichever is the point of contact with the ground, the angular speeds and the forward going speeds are such that the point of contact with the ground at any point has a zero velocity. And because of that, in this case where it is free rolling, the friction force becomes equal to zero. Because if you think, if when there is rolling, pure rolling, if there was a friction force, then the velocity would change. But the velocity does not. Once it reaches the pure rolling condition, it remains at a constant velocity. Of course, keep in mind that this is when there is pure rolling. In actual rolling scenarios, we see that a rolling ball or a rolling disc eventually comes to a rest. And that's because once it reaches pure rolling, there is still some amount of frictional losses that happen, ever so slightly. And one can hypothesize that what happens is that it slips a little and goes back to rolling, again slips a little, goes back to rolling, and that sort of slowly takes away energy from the system and eventually comes to a rest. But here we are considering pure rolling, so in this case what will happen is that when V becomes equal to omega r, then pure rolling ensues, and at that point the velocity remains constant, the angular velocity remains constant, and they satisfy this relation V equals omega r. We are referring this to as Vx just because we have chosen this forward direction as the positive x direction. So so we did this derivation in our last video, and in fact we were able to also find out the time where from the initial condition, the time when the linear velocity and the spinning velocity become the same, and that time is given by this t star. And we did this calculation for a disk whose moment of inertia about its center of mass is half mr squared. Now we'll continue with this with a few more calculations, and you can refer to this previous video to get more details of this calculation where I have shown this calculation. But here what I want to do is point out a few more features, because one of the themes of these videos is to delve into these problems a little bit longer, to understand some of the nitty-gritty details and to in the process get our conceptual understanding better. So one question that comes up is that, okay, so t star is the time when the velocity becomes equal to omega r. What is the velocity at this point? Okay, so that can be found out quite easily, because we know that the velocity x is equal to v naught minus mu gt. So and so it's going to be at the point when, therefore, when rolling, that is pure rolling, starts at t equals t star, what's going to happen is v will be equal to v naught minus mu g t star. So it's going to be v naught minus mu g, and t star is v naught minus omega naught r divided by 3 mu g. So we cancel the mu g's from the numerator and denominator, and we have v naught minus 1/3 v naught, so 2/3 v naught, plus 1/3 omega naught r. So this is going to be the velocity. This is the velocity, linear velocity of disk when rolling or pure rolling starts. Okay. Now similarly, we can find out the angular velocity when pure rolling starts. So similarly, omega is equal to omega naught plus mu mgr t star divided by IC. So simplifying, this is omega naught plus mu mgr, and IC is half m r squared times t star. So t star, so let me just v naught minus omega naught r divided by 3 mu g, right? So this is going to give us omega naught plus, so I'm going to cancel this mu and g, right? And I'm going to cancel this m as well, and we can cancel this r. So you have 2/3 r 2/3r times v naught minus omega naught r, right? So the angular velocity then becomes equal to omega naught plus 2/3 of v naught over r minus 2/3 of omega naught. So continuing with this calculation, this then becomes 1/3 of omega naught plus 2/3 of v naught divided by r. So that's my angular velocity. So this is the angular velocity of disk when pure rolling starts. Right, and now we note that now verify that v is equal to omega r when pure rolling starts. So we need to be able to verify that indeed when the pure rolling starts, the linear velocity is equal to omega times r. So we see that, observe that omega times r, so from here, right, omega times r is 1/3 of omega naught r plus 2/3 of v naught, which is nothing but this expression, so which is equal to v. Therefore verified. Right, so so that's another observation. Now another thing that I would like to point out is the rate at which the velocity is decreasing and the rate at which the angular velocity is increasing when the disk moves from slipping to rolling. So note that Vx is equal to V naught minus mu gt. So therefore slope is negative mu g. So the slope with which the velocity is decreasing, and omega is equal to omega naught plus mu mgrt divided by IC. But since we are going to plot omega r and not omega, so what we'll do is we'll just multiply both sides by r, and we'll have mu m r square g t divided by, and now we'll substitute this half mr squared, so that's going to give us omega naught r plus mr square is going to cancel, so plus 2 mu gt. So therefore slope is 2 mu g. So if we sketched or if we plotted the translational velocity and the rotational velocity of the disk of the cylinder, and let's say, because in this case we are starting off with V naught greater than omega naught r, if this drops by a slope like this will have a slope greater, it's going to have 2 times the slope. So the angular velocity rise is going to be sharper, and then they will reach this point beyond which we are going to have V equals omega r. So the linear velocity goes this way, the angular velocity goes that way, and then once the rolling condition is reached, then the velocity and the angular velocity don't change anymore. So this slope is going to be 2 times this slope. Okay. So that's another observation. Finally, the third observation that I would like to make is that fundamentally, when there is slipping, there is loss of energy, because it's friction which is taking away energy from the system. Once the system reaches pure rolling, it is the system becomes a lossless system. There is no energy is lost, and we are talking about pure rolling. So when we start with this kind of a scenario where the velocity is greater than omega naught r, initially there is friction forces and there is slipping at the contact point, and so energy is continuously being lost. And then we reach a point where it goes into pure rolling, and there the energy is conserved. But we should be able to prove that because throughout the slipping energy is lost, then the energy level here must be less than the energy level at the starting point, right? So let's say that the energy level over here is E1 and the energy level over here is E2, then E2 must be less than E1. E refers to energy level is equal to T plus V, the kinetic energy plus the potential energy. Okay, so the mechanical energy at E2 must be less than the mechanical energy at E1, and let us try to prove it. Okay, so when the rolling without the slipping starts, so initial energy is equal to half mv naught squared plus half IC omega naught squared. In this case, we don't have to worry about the potential energy because the disk is moving on a horizontal surface. So we have half mv naught squared plus half times half m r squared omega naught squared. So that is half m v naught squared plus 1/4 m r squared omega naught squared. So that's the initial energy, and we should be able to prove that when the system reaches this rolling without slipping, at that point, so this we would say is E1. Okay, and we should be able to prove that when the disk reaches this rolling without slipping condition through slipping, the energy E2 at that point is lower. So let's find out E2. So E2 is going to be equal to half m and then the velocity at so I'm going to call it V star. So this is, so here I would say that the velocity is V star and omega star. Okay, so half mv star squared and half IC omega star squared. So this is the expression for E2, and so we have half m, and we'll substitute the expression for V star, which is 2/3 of V naught plus 1/3 of omega naught r squared. And then we have half IC is half mr squared, and omega star is 1/3 of omega naught plus 2/3 of V naught over r whole squared. Alright, so we have half m 2/3 V naught plus 1/3 omega naught r whole squared plus I'm going to factor out r square from this expression, and I'll have 1/4 m. This r square in the denominator will cancel the r square in the numerator, and I'll be left with 1/4 m outside the parentheses, and inside the parentheses it's going to be 2/3 of, oh sorry, this is not V naught squared, it is V naught, 2/3 of V naught plus 1/3 of omega naught r whole squared. Okay, so the total is then going to be half m plus 1/4 m, so that's 3/4 m times 2/3 V naught plus 1/3 omega naught r whole squared. So this is E2. So we want to prove that E1 is greater than E2, right? So let us see if this is actually true. This has to be the case if all our algebra is correct and our analysis is correct, because clearly energy is lost during sliding friction. So let us assume that this is true, and then we will show that this inequality is indeed correct. So if E1 greater than E2, then half m V naught squared plus 1/4 m r squared omega naught squared is greater than 3/4 m times 4/9 V naught squared plus 1/9 omega naught squared r squared plus 4/9 V naught omega naught r. Okay, or in other words, let me just cancel m from both sides just to make the expression simpler. So it's going to be half V naught squared plus 1/4 r squared omega naught squared is greater than, must be in that case greater than 1/3 of V naught squared plus 1/12 of omega naught squared r squared plus 1/3 of V naught omega naught r. Okay, so if this is true, then we must have half minus 1/3 is going to be 1/6 V naught squared. 1/4 minus 1/12 omega naught squared r squared is going to be 1/3. And then I'm going to bring this to the left. 1/3 V naught omega naught r is greater than. So this must be true. If indeed the energy is lost in the process. So let me just multiply both sides. Let me just multiply the expressions by 6. So we are going to have V naught squared plus 2 omega naught squared r squared minus 2 V naught omega naught r is greater than 0. Okay, so note that I can write this as V naught plus omega naught r whole squared plus omega naught r, oh sorry, this is minus, plus omega naught squared. This is just algebra. I took this one, I split this into two parts, omega naught squared r squared. I used one of them and combined it with this 2 V naught omega naught r to form this whole square. So V naught minus omega naught r whole squared. And what I was left with was this omega naught r whole squared, which is omega squared r squared. Now I see that the left hand side is a sum of two squares. And so clearly this is going to be greater than 0 as long as, so note that indeed left hand side is greater than 0 since it is the sum of two squares. So indeed the energy with which it started was greater than the energy E2 once the disk reached the rolling without slipping condition. So we have proven then that indeed energy is lost and from its initial kinetic energy, and the loss happens until the point it reaches the rolling without slipping. So one of the things that we see with this scenario that we have analyzed is that the friction force, so let me just do a quick recap. We noticed that the friction force that the ground provided due to the contact with the disk at the time of slipping was such that it reduced the velocity and it increased the angular velocity. Although it increased the angular velocity, but overall the energy reduced. Okay, so this increase in angular velocity to reach pure rolling as the linear velocity decreases does not mean that the energy is remaining constant or is increasing. The energy is actually decreasing. So while the energy is decreasing, the velocity and the translational velocity and the angular velocity, they are linearly changing with time, so that they reach situation of pure rolling. And the friction force is automatically facilitating that. It is acting in such a way that the velocity decreases and the angular velocity increases. It is almost like the friction force is trying to ensure that the system goes into a pure rolling condition from a slipping condition. We will see that when we go to the scenario 2, that is when V0 is less than omega naught r, the same thing happens. That is, the friction force again appears in such a way that it will try to make the linear velocity become equal to the angular velocity times the radius, so that pure rolling happens after some slip. And so it's almost like whenever there is slip, the friction force very intelligently shows up in such a way that it tries to make the slipping go away. It's almost like when the disk slips on a horizontal surface, its interaction with the surface is such that it likes to go to a pure rolling condition. And the pure rolling condition is always an attractive configuration or an attractive condition for the disk to be in. And the friction forces, they appear in a way to take the disk in that to that type of motion, that is the pure rolling motion. So we'll verify that when we do an analysis of scenario 2, where the initial linear velocity is going to be less than the initial angular velocity times r. So that's it for this video. Thank you so much.